Any questions about this? Okay. So because cosine is between 1 and -1, we can always say that the directional derivative in the direction of u of f at p is less than or equal to negative the magnitude of the gradient of f at p, and is less than or equal to the magnitude of the gradient of f at p. Just because this is always going to be less than -1, bigger than -1 and less than 1. Which tells us that any direction that we go in, if here's my u, the directional derivative of f in this direction will always be less than the directional derivative in the direction of the gradient itself. So if here is my gradient, if I look at the directional derivative in this direction, which corresponds to the magnitude of the gradient, that will always be less than the directional derivative in the direction of u, and that will always be bigger than the directional derivative in the negative direction of the gradient. Any questions about this? Okay, so in other words, the gradient vector points in the direction of maximum rate of increase and the maximum rate is the magnitude of the gradient. And similarly, f decreases most rapidly in the opposite direction, and in the opposite direction, the rate of decrease is that. Now, if we have a surface in 3 dimensions, and we look at the level curves of this surface, so maybe this is, this over here is f xy is equal to z, and this over here is f of xy is equal to 2, f of xy is equal to 1, and f of xy is equal to 0. Then the gradient is always going to be orthogonal to these level curves. We can first think about what happens if we go along the level curves. Well, along the level curves, we're not actually changing our f. So along them, the direction in the u direction, if u is going in the same direction of the level curves of f at some point p, is going to be 0. But if we want to know how we can best change, how we can change f the fastest, we're just going to leave the level curve directly, walk right off of it, and that will be the fastest rate of increase. And if we walk in the opposite direction, that will be the fastest rate of decrease. Any questions about this? So in general, the gradient is always orthogonal to the level curves, like this, or normal to the level curves. Okay, I'm going to skip this, so let's go through this again. The directional derivative of f in the direction u is the same as the magnitude of the gradient times cosine of theta. The gradient points in the direction of fastest rate of increase, and that increase is the magnitude. Its negative points in the fastest rate of decrease, and the rate of decrease is the negative. And like we said, the gradient is normal to the level curves of the surface of f. Here we have a picture where all the gradients are indeed orthogonal to the level curves. So now they give us an example. Let f of xy be x to the 4th y to the -2 and p equal to that. Find the unit vector that points in the direction of the maximum rate of increase and determine the maximum rate. So first we need to find the gradient. That will be the direction of maximum rate of increase. To find the unit vector, we just need to take the magnitude. And to determine the maximum rate, we also just need to take the magnitude. So they tell us f xy is equal to x to the fourth y to the negative 2. And p is equal to 2, 1. So the gradient of f at xy is equal partial of f with respect to x, partial of f with respect to y, which is going to be equal to 4x to the third times y to the negative 2, and negative 2y to the negative 3x to the fourth power, which means that the gradient of f at 2, 1 is going to be equal to 4 times 8 times 1 and negative 2 times 1 times 16. And this is equal to 32 and negative 32. So this is the direction of maximum increase. Now, the unit vector is going to be 32 comma negative 32 over the square root of 32 squared plus 32 squared. And the magnitude of this at the point 2, 1 is going to be the square root of 32 squared plus 32 squared. So this is going to be the rate of increase. Any questions about this? Okay. Let's do another example. They tell us that the altitude of a mountain is at the point xy is given by f of xy is equal to 2,500 plus 100 whatever. And they want us to find the direction of the derivative, the directional derivative at this point in the direction u, where u is making an angle of pi over 4 with the gradient. And they want us to interpret the derivative. So first we need to find the gradient. We then need to find its magnitude and multiply it by cosine of pi over 4 in order to find the directional derivative in the direction of u. And the interpretation would be that if we walk in the u direction, the change in the mountain will be going up apparently because it's going to be positive, and the rate of increase is going to be at 116.7. So f of xy is equal to 2,500 plus 100 x plus y squared e to the negative 0.3y squared, negative 0.3y squared. So the gradient of f at xy is going to be partial with respect to x, partial with respect to y, which is going to be equal to, so the x is going to be this, that, and that. So that's going to end up being 100 e to the negative 0.3y squared, comma. And the y is going to be this, and this, and this, and we clearly have a product rule. So in the y direction, we're going to have 100 times 2y e to the negative 0.3y squared plus y squared plus Oh, and we also have the x. Okay, so let's add that actually for 1 second. Okay, plus 100 e to the negative 0.3y squared. Okay. And then plus 100 y squared e to the, oh, sorry, some mistakes over here. There is a point, 1 second. Yeah, over here there is a negative, no, nothing there. Okay, over here there's an x. And then we are going to have, erase this, x times -0.3 -0.3 times 2y. Okay. And then we're going to have plus 100 y squared e to the negative 0.3y squared times negative 0.3 times 2y. Okay. So now, let's see. Yeah, so let's plug in the values. So we are at the point -1, -1. So we're at the point -1, -1. So plugging that in, we are going to get 100 e to the negative 0.3, comma, and then over here we're going to get negative 100 times 2 e to the negative 0.3, and then the second line we're going to have a negative from here, a negative from here, and a negative from here, so we're going to get minus 100 e to the negative 0.3 times 2, and then we're going to get plus 100 e to the negative 0.3 times negative 0.3 times 2. Sorry, and this negative cancels with the negative from the y. So then we're going to end up getting 1 second. Oh, and there's a negative. There's a negative. There's a 0.3 over here. Okay. So these are going to cancel. And we are going to end up getting 100 e to the negative 0.3 and negative 200 e to the negative 0.3. Yeah. And so the first one is 74 and the second one is negative 148. So 74, negative 148. Okay, so this is our gradient. Any questions about this so far? So the directional derivative then in the direction of u of f at the point P is going to be equal to the magnitude of 74 squared plus 148 squared times cosine of pi over 4. And all right, and that's it. Any questions about that? Okay, so let's continue. We're gonna skip the this part and continue with this over here. So you can also use the gradient to find normal vectors to tangent planes of higher dimensional surfaces. So we can think of a surface f of x, y, z is equal to w, higher for three independent variables, one dependent variable. And then we can think of a level surface, this equal to k, some constant. And that would give us some surface in 3 dimensions. Let's say it looks like that. Now, if we take the gradient of f at some point P, that's going to be f with respect to x at P, f with respect to y at P, and f with respect to z at P. This over here is going to be normal to the surface, the same way the 2-dimensional gradient is normal to level curves. So this is normal to the surface, which means if we have that the point P is equal to A, B, C, we can use this to find the tangent plane. And the tangent plane is going to be the normal vector dotted with x minus A, y minus B, and C minus Z, Z minus C. Which is going to be f with respect to x at P, x minus A, plus f with respect to y at P, y minus B, plus f with respect to z, P, z minus C. Now, in the case that we were doing before, we had that f of x, y is equal to z, which would mean that f of x, y minus z is equal to 0. And we can now rewrite this in the form f of x, y, z is equal to 0. And taking the partial of f's will give us, so if we try putting that into this equation, we will get the tangent plane that we found before. Because the partial of f with respect to z, well, what's the only z here? It's just this. So we would get f with respect to x at P, x minus A, plus f with respect to y, P, y minus B, minus 1, because that's this over here, times z minus c is equal to 0. Which is what we had for the tangent plane before. So this is a generalization. Any questions about this? Okay. So let's continue with an example. They want us to find the normal vector and tangent plane for the equation of the surface 4x squared plus 9y squared. 4x squared plus 9y squared minus z squared is equal to 16. At p is equal to 2, 1, 3. Okay, so first we need the gradient of this, so we can say f of x, y, z is equal to 4x squared plus 9y squared minus z squared. And the gradient of f at x, y, z is going to be equal to 8x comma 18y comma negative 2z. So the gradient of f at the point 2, 1, 3 is going to be equal to 16, 18, and negative 6, which is also our normal vector. So our tangent plane is going to be 16 times x minus 2 plus 18 times y minus 1 minus 6 times z minus 3. And that's going to be our tangent plane to that surface. Any questions about this? Okay, so in summary, we spoke about the gradient. We did not talk about this, so it won't be on the test. We spoke about the equation of the directional derivative in the direction of u. We said that we can find this directional derivative by dotting the gradient with u, so long as u is a unit vector. We also said that we can use this formula, just take the magnitude of the gradient times cosine of theta, where theta is the angle between the gradient and u. We said that the gradient points in the direction of greatest increase, and the rate is the magnitude. And the negative of the gradient points in the direction of fastest decrease, and the decrease is negative of the magnitude. And the gradient is orthogonal to the level curves. And finally, we saw this formula for the tangent planes for a surface like this. Any questions about this? Okay, so the test is going to start from functions of several variables. For limits and continuity, you do not have to know the epsilon delta definition, but you do have to know how to show that a limit does not exist by choosing paths to approach a point. Or you need to show how a limit does exist using polar coordinates. Of course, you have to know how to take partial derivatives, find the tangent plane and the linearization at different points, know the properties that we talked about gradients and directional derivatives. And next class, we're going to review for exam 3. Are there any questions about any of this? Okay, then I think I'm going to stop here. Have a nice day. Bye.